Good day, I'm Dr. T, and welcome to my dining room table. So I'd like to continue talking about chemical reactions involving organic compounds, but I'd like to take a little bit of a detour. So far we have talked about reactions that involve pairs of electrons. So we've talked about, say, nucleophilic substitution, in which case you have your nucleophile, which will have typically a lone pair, and you'll have an electrophile, and your nucleophile will attack the electrophile, and you get yourself a new bond. You have a pair of electrons moving. We talked about addition reactions, in which case you have your double bond, and remember, bonds are pairs of electrons, and of course we could then take something like, an HX, which would be, hydrochloric or hydroiodic acid, something like that. And then the electrons from the bond, those go ahead, they do the attack. They're working in concert, so it's a pair. The electrons from this bond, which are being displaced, move over. Once again, that's a pair of electrons. And then we get something like a carbocation. Of course, there's a couple more bonds over here. So, there's more than what I'm drawing. But this guy still has, 3 bonds. We have our X minus over here. That's now a very nice little nucleophile. It's going to go ahead. It's going to bond over there, and now we get our new addition product, which of course is still in the middle of a molecule of some sort. Pairs of electrons. We even talked about elimination, a couple different styles of elimination, but we basically can just run this in reverse. We can have, something like this. And in this case, hey, this guy can just decide to split. It's going to become an anion. These electrons are going to go over there. And then in that process, we're going to get H+, the double bond. I'm kind of simplifying this a little bit. X minus, and then those will form, an HX. All of these cases have involved double bonds. And you notice how they all involve these two-headed arrows. Now, I want to talk about our radical reactions, and these involve radicals, as the name would blatantly suggest. Radicals are odd-numbered electron-containing compounds. So in this, or I should say atoms. So in this case, hey, I could have something like Cl2, which would be ClCl. And I can hit this with some UV light. And when I do, I'm going to get a pair of Cl radicals. They're not minuses, they're not cations. It's so tempting to write Cl minus because we're so used to seeing them. In this case, this is Cl radical, which is denoted by a dot. That horrible thing is supposed to be a dot. This is not an ion. This is actually a neutrally charged atom. As such, UV is non-ionizing radiation. It doesn't mean it's safe. It doesn't mean it won't hurt you, potentially. You have melanin in your skin and wear sunblock for a reason. But it doesn't actually form an ion. It likes to do radical reactions. So we can see a lot of these things, especially if you look at the yellowing of plastics. So I'd actually like to look at a couple of classic radical reactions and just kind of look at how they flow. And the first one's actually going to start off with this one. And the way we denote, by the way, the radicals doing what they're doing is we'll do a single-headed fishhook, or kind of a harpoon, I've sometimes called it, or heard it called. So see how it's like a fishhook where it only has the one head. It's an actual fishhook. Okay, so this is the initiation step. At this point, you need something like ultraviolet light is a classic, but there are certain chemicals that like to form radicals themselves. Hydrogen peroxide is a classic case. This is why it's used to disinfect wounds, because it forms lots of radicals and can kill bacteria. This is also why it's not recommended to disinfect wounds under most circumstances, because it causes radicals and kills your own healthy cells. So too much collateral damage. Soap and water is usually recommended under most circumstances, but I'm a chemist, not a physician. I'm not giving medical advice. Talk to your medical personnel on how to clean your own wounds, kind of thing. Okay, so we've got this one. Now, with these radicals, these are very, very reactive. Electrons like to have pairs. So this can react with something else. And so I can have, say, a methane over here. And I can have one of my chlorine radicals. And it can go ahead and it can do a reaction with, say, the hydrogen over here, but in doing so, it's going to split apart that bond. And so now I'm going to have CH3 radical and HCl. So I've created a product, but I've continued creating a radical. And this allows me to kind of this continuation phase. I can get this chain reaction going. So now I've got this guy. I can have this guy going. And it can meet up with, say, a Cl2. And it can cause the radical to go. And now this guy can give me CH, that monstrosity is a C. That's an H, that's the Cl. CH3Cl plus Cl radical. And you can see how this can continue in a chain reaction. And so with this one, a single photon of ultraviolet light or a single initiating molecule that's able to form a radical can cause a lot of reactions because this is just going to keep going and I can do other things. Now eventually it's going to hit a termination step and that's typically where two radicals meet. So I could easily have a scenario, let's see if this will actually fit on my paper. Yes, I can see it. So I could have a situation where I have, say, this guy and he meets up with another one like him and I'm just flipping the orientation so they line up nicely. And we do the harpoon thing, and now we get ethane. And if you're hearing any popping, this is the 5th of July, hence the random explosions outside. Okay, so yeah, this is a reaction. So this generally will go for an initiation phase, which is the formation of a radical. You'll have a whole bunch of chain reaction phase, where the reaction just keeps going and going and going, and then you'll have a termination phase. And this can be basically anywhere where the radical goes away. Okay, so let's look at a couple other examples. A classic radical reaction is actually combustion. I'm going to do one of the simplest combustion reactions because radical reactions can get insanely complicated, and I have made the mistake of trying to draw even a slightly more complicated one. So let's go H2 and O2. Now, interestingly enough, oxygen, if you actually look at the way its electrons are drawn, this guy is the Lewis structure for oxygen, this fairly standard Lewis structure. However, if you actually look at the molecular orbitals, that second bond isn't really that much of a bond. It's already going towards radical itself. So it's kind of self-radicalized. Okay, so we've got ourselves these guys, and under high heat, if these guys collide with enough force, then you can break one of these bonds in a way that forms radicals. So we can collide them at really high force, and now I can get a pair of H radicals. Then these guys can interact with my oxygen. And at this point, I can now start forming something like this guy. He's got a radical on him as well, so I might have this guy doing with an H there. By the way, the reason I'm not reacting with him is presumably there is a greater abundance of the non-radical form. You only get a small number of radicals at any given time, so the odds of a radical meeting up with a radical are typically rather low until the continuation, the reaction just keeps going and going and going. But, they're definitely not zero. These reactions will stop. They will meet in with a radical, or just won't find anything to react with. Okay, so this guy can do its reaction. So now I get hydrogen peroxide plus H radical. I could have this hydrogen peroxide meet up with another H radical. And so now I get HO radical, or hydroxyl radical, and then some water. And then I can have this HO radical meet up with an H there. And you can basically see where this is going. And we're just going to keep going until we run out of products, or we're no longer really able to keep doing this. HOH, which, you know, that's H2O. Okay, that thing's a bond. So yeah, this is combustion. When we're looking at, say, firefighting, which is breaking up combustion, we've got actually 4 different ways to tackle this. One is simply to get rid of one of the 2 reagents. So this guy, this would be our fuel. It's the reduced one. It's the one in the process that's reacting with the oxygen. You've got your oxygen, or I should say oxidizer, because when you're looking at this guy, if you're counting electrons and kind of who's the electronegative one, we're doing oxidation numbers. In that case, the hydrogen is going from a higher oxidation number to a low oxidation number to a higher one. It's being oxidized, whereas the oxygen is going down. It's being reduced. So this is a oxidation reaction, as was mentioned in a much earlier video. But with that said, so I can remove the fuel, I can remove the oxygen, I can also remove the heat. I can keep this low enough that when I do have termination reactions, there's not enough heat in order to reform new radicals. And once that happens, it's done. Alternatively, there's a 4th way that we don't normally talk about. So normally we think of the fire triangle, you know, fuel, oxygen, heat, or I should say oxidizer and heat. But in reality, it's actually the fire trapezoid, because there's one more point in that reaction. The halon fire extinguishers, which are all halocarbons, so contain chlorine or fluorine or whatnot in them. Those are going to be able to cause reactions that will disrupt the chemical reaction here. They like to react with the radicals, but they form structures that don't want to continue on. They enhance the termination step, essentially. These aren't very common. They're definitely not the greatest things for the environment. They mess with ozone, etc. But they do have some very nice properties. They're able to work in very low concentrations. So you'll sometimes see these in restaurants, kind of the giant spouts over the people's heads on the area might be these. They could also be several other different chemicals, and you see them for military applications where you need a high ability to fight fires with a small, package space, kind of thing. Okay, so this is combustion. Now, the interesting one, if we look back at the one I did earlier, so in this case, let me see if I'm in view, you'll notice how I made a side product over here. When it comes to combustion, if I've got carbon going on, I've got this guy. This guy is going to be part of my carbon-carbon reactions. So if I've got, say, a carbon fuel, I've got methane or hexane or anything else, if this is reacting not with chlorine, but with, say, some radical oxygens, then I can get these interesting termination steps where I get new molecules. Now, one of the molecules I can get when I do this is going to be aromatics or benzene. The interesting note, let's see if I can draw a hexagon. The interesting note on this one is that this is a particularly stable molecule. Wow, that looks hideous. This is a particularly stable molecule, so it's very difficult to turn this into a radical because of that aromatic ring. You'd have to break the ring in order to make this into a radical. As such, you need very high temperatures in order to break this apart. If you have a low temperature fire, you're going to get lots of soot. Soot is going to have lots of aromatic rings in them, whether or not it be benzene itself or other compounds that contain one or typically multiple aromatic rings. This is why if you've got, say, a stove, you might very well be monitoring the temperature of the fire, especially in the chimney, to make sure it's high enough that you're not producing soot, because that's how you get to a chimney fire. You build up soot on the inside of your chimney. That is a carbon fuel source, and if it does get hot enough to ignite it, now you've got fuel going up your chimney, and you don't want fuel up your chimney. That's how you catch it on fire. Additionally, if you were to say smoke, that is a low temperature fire, and all that tar that's being talked about when we talk about smoking and why it's absolutely horrible for your health and effectively suicide, that is because of incomplete combustion. You don't have enough oxygen, you've got leftover carbon, they're doing a weird termination step where you're forming aromatic compounds, which, one, literally clog up your lungs. Weird particles in your lungs are not good. And two, aromatic compounds, as I'll talk later, resemble that of the nucleic acid bases within DNA and can cause issues there. And by issues, I mean lung cancer. So, take-home messages from this video. Radical reactions, they're important. And two, don't smoke. A quick aside when we're talking about combustion. A combustion will almost always, or really it always happens in the gas phase. So if you have a gas reactant, so you've got a fuel that's, methane or something that's a nice gas, it reacts with oxygen, gas, you've got a gas phase reaction, great. If you have a liquid fuel like hexane, this needs to be evaporated and converted into the gas phase. In your car, you have fuel injectors that will create a thin aerosol. The tiny droplets will then easily evaporate. If you have a particularly vintage car, then you'll have a carburetor, which is basically an area to evaporate the fuel, get that into the gas phase, then put that into the piston, which is what your carburetor does. If you have a solid fuel, this isn't going to typically evaporate. So what you end up doing is what's known as pyrolysis, where you put it under high temperatures. You start doing radical reactions, and you start forming small molecules that may or may not be radicals themselves, but are going to be ones that can be gas phase. So if you say burn wood, one of your products is actually going to be carbon monoxide. And then the carbon monoxide is able to burn. So you use some of the heat from the combustion of the gas phase material to pyrolyze your solid fuel, and then that creates more gas phase fuel to then continue combustion. That's why when you've got, say, charcoal, you have to put a pretty good light to it to get it going, because you need to do the pyrolysis. If you put some paper down, it's thin, just a little bit of heat will do a little bit of pyrolysis, and that gets the things going, so you get this nice pyrolyzed material that gets the fire going. Or you could use a liquid fuel like lighter fluid if you're trying to get your grill going. The consequences, of course, though, some of these products from pyrolysis are going to be particularly unpleasant. So things like carbon monoxide, you want to make sure you're venting fumes out if you have an incomplete combustion. That's where you don't have enough oxygen to burn all of your materials. So whether or not it be, the products from pyrolyzed solid fuels or from liquid or gas fuels, if you don't have enough oxygen, you don't burn them completely, you get weird side products, things like the benzene, or things like carbon monoxide, which is why if you do combustion in your home, aka you have gas heat, you need a carbon monoxide detector, just in case you have poor combustion and a ventilation system that's not getting the fumes out of your house, because that can be pretty unpleasant. So with that said, have a wonderful day, and I'll see you in later videos.